I guess I'm live. Hi, welcome. Thanks to Sport Techie for inviting me today, and I certainly look forward to talking with you this afternoon. I'd like to start off my presentation with a bit of my background and how I got to this point. And we'll look at some motion capture from the past, and I'm going to then talk about motion capture, the new types of motion capture and motion capture for the future powered by AI, artificial intelligence. In each case, I'm going to try and give you a couple of examples of how we use it for Team USA. I hope to answer some questions in the session later on, so let's get going. Okay, a little bit about my background. My undergraduate was Bachelor of Electrical Engineering. I have a master's degree and a PhD in biomechanics from Arizona State University. I am an Olympian in gymnastics for Australia. I did compete in 1976 in Montreal. I was also on the team for 1980 in Moscow, but unfortunately that was the boycott year, so I didn't get to go. So my combination of engineering and sport brought me to the world of motion analysis. And I've been developing motion analysis systems in the field for about 40 years now. Currently, I'm the Director of Technology and Innovation at the US Olympic and Paralympic Committee. Before we actually get into the meat of the presentation, I'd like to do a couple of definitions. The difference between motion capture versus motion analysis. Motion capture is just simply capturing the motion and digitizing the data, bringing it into the computer. And typically that's used for like games and movies and that sort of thing. But the next step is motion analysis. That's where we take that motion data and actually calculate from it. We use it in biomechanics, which is the study of human motion using physics, anatomy, and physiology. So we quantify the data and calculate parameters from it. So the steps in motion analysis, which you can see there, are first we capture the motion with video or sensors. Then we compute the physical parameters of the motion, and they could be joint angles, positions, paths, velocities, accelerations, and similar parameters. Once we've got the calculations done and we've got all the parameters saved, we can then go ahead and use statistics, of course, to do our analysis. So we could compare to a database. We could compare a parameter using a t-test or analysis of variance. And if we don't have a database of the world's best, for example, we could compare you to you. We could compare your current performance of a skill to what you've done in the past, and maybe compare your best to your not so best. So anyway, that's the way that we can use motion analysis, and I'll give you some examples, excuse me, by looking at past, present motion analysis systems from my point of view, from my experience. So as I said, we're going back 40 years here. So back to 1980 when I was doing my master's degree at Arizona State University while I was training and working as assistant coach in gymnastics on the Arizona State team. Unfortunately, that was the boycott year, so I didn't get to go to the Olympics. But on the other hand, I was very, very lucky to be able to complete my master's degree while training with a bunch of great gymnasts. So back then, the Human Performance Lab had a low-cam camera, a digitizing tablet, a 16-millimeter projector, and a state-of-the-art computer, which had a massive 64K of RAM. And anyway, the problem was these were not connected to one another, and there was absolutely no software. So part of my job to get my master's degree was to learn how to program the computer and connect this all together. So I wrote some basic code that effectively allowed me to digitize a handspring front somersault vault, which is the animation that you're seeing at the bottom of the screen there. Now, in this case, digitizing means basically putting the crosshair cursor on every joint, one by one, for every frame. So very laborious process. But nevertheless, it was able to create these stick figures, as you see here, and I was able to compute the velocity coming in and the velocity coming off the horse, and how far they went, and all the key performance indicators, of the vault. And lucky for me, that was enough to get my master's degree. So that was digitizing with film. After I finished my master's degree, I found a job at the U.S. Olympic Training Center for the U.S. Olympic Committee in Colorado Springs, working in the sports science department as a research engineer. And my experience writing a digitizing program for film helped in the fact that we were able to do it for video now. Although back then we had the IBM XT and we had a very high-end video cassette recorder that we were able to control and capture frames from and put them on the screen of the computer. And what that allowed me to do now was from video what I was doing from film before. The difference being now, we didn't have to send the film out to get developed. Excuse me. And we could basically capture the data or capture the videos during the training session during the day. We'd work on it in the evening, digitizing overnight, and be able to present the key performance indicators, the parameters, the data, the graphs to the coaches and the athletes the next day and show them how their performances were differing from one trial to another. So that proved to be very advantageous to us. And in fact, we found that that technology was really on the cutting edge and was wanted by a lot of other people. So we basically formed our own company, a coworker and myself, left the US Olympic Committee in 1987 and formed a company called Peak Performance Technologies. There we developed two different types of motion analysis systems. We expanded to 3 dimensions. So now we had multiple cameras instead of just one camera. And with 2 cameras, basically you can triangulate a point. And so you can calculate not just its XY position, but also its X, Y, and Z position simultaneously. The principle there was to use a calibration frame, and that's this Sputnik-looking device right here. It has known points, and so you digitize all the known points. You tell the computer where those are in space, and then that allows it to understand where an origin is, where the reference frame is, and what basically it allows it to transfer from pixels to meters. But you still had to manually digitize from each view. And now instead of having one camera, you would have 2 cameras or 3 cameras. So this is very, very laborious process with 3 dimensions versus 2 dimensions. So at the same time, we developed an automatic tracking system that would use cameras, and now it would use the reflective markers. So you can see the reflective markers fluorescing when a floodlight is shined upon them. Basically, the computer could find those bright spots and track them automatically. And so this cut down the labor from doing the manual digitizing to doing the automatic digitizing, made it much faster, but still it was not perfect because if a marker got hidden, for example, if you put your hand behind your back and the cameras couldn't see that point, then they can't track them. So the solution to that is multiple cameras. But the downside of multiple cameras is the fact that, of course, it's going to get more expensive and so more complex because you've got more cameras to set up. So it's fast, but not completely automatic, and it becomes complex. Now, we weren't the only ones at that time. We were a pioneer, but there were other companies, Aerial Dynamics, Motion Analysis Corporation, Vicon, and Qualisys, to name just a few companies that were around doing motion analysis, automatic tracking at that point in time. Now, that being said, as I said, I was a little frustrated with the fact that we were not able to track automatically completely through a whole session. You have to come back and do some post-processing. So I was looking around for some other technologies. And in fact, in 1992, I did find a technology. It's electromagnetic technology. You have small sensors that have 3 coils of wire, and those coils of wire have a magnetic field induced in them from a transmitter, and they can calculate X, Y, and Z, and not just X, Y, and Z, but also pitch, yaw, and roll. So that's what's called 6 degrees of freedom, and that was a pretty exciting technology. As it evolved, it got faster and faster, and we were able to capture at 240 samples per second, and we were able to do it in real time. The beauty of doing it in real time is not only did you get the data quickly, but you could also use it for doing what we call biofeedback training, where, for example, you can see we were doing it with golf as well. You could see that how much they've turned. And when they turn, a beep would sound. And so the golfer or the athlete would know that they've got into the range that they're supposed to be in. So anyway, we developed that. And in 2004, we met Greg Rose and Dave Phillips. And you've heard of Greg Rose talking earlier today. And we developed a system called TPI 3D. In fact, that was the motion capture system that Greg was showing earlier. But we developed that and teamed up with TPI. And the new company that we had at that time was called Advanced Motion Measurement. We started out in research, actually, and we started out with clinical biomechanics, gait analysis systems, reach and grasp, and different types of measurements. But quickly, once we met Titleist Performance Institute guys, we gravitated towards golf. Now, one example of a typical type of algorithm that we developed while we were doing golf swing analysis was called the kinematic sequence. And that's a very important basic notion in biomechanics. And that is that you develop your speed from the ground up with the big muscles, transferring it across each joint to the smaller limbs and finally to the end point, which could be a bat or a club. In this case, I'm demonstrating it for a golf swing. And you can see that from the graph, the vertical graph is rotation speed of a body segment in degrees per second. And the bottom axis, or should I say the x-axis, is in fact time throughout the swing. And the four curves, the red is pelvis, the green is the thorax or rib cage, the blue is the arm, and the brown is the club. So here we've got backswing, we've got downswing, and we've got follow through. So what's really exciting and what we discovered is that in all elite golfers, and I say all elite golfers, they have slightly different shapes, but they're very, very similar. They all accelerate and then decelerate. The big segment first, in this case, the pelvis, the red curve, then the green curve, which is the rib cage, the arm, and finally the club. And you see this acceleration, deceleration signature that really shows you how energy is transferred from one part of the body to the other. And the gain across each joint is how much the curve jumps from the one to the next to the next. So the difference. So the beauty of this is you can really tell the difference between an amateur and an elite or pro golfer. And we presented this at the World Scientific Congress of Golf in 2008, showing those differences. So you're able to analyze a golf swing and you can find out power leaks, you can find out which part of the body is not doing its job, and so on. So that was a good example of how we were able to use this motion capture technology in golf. And by the way, I'll show you in a minute that it applies to many throwing sports, whether it be baseball or javelin, in fact. So unfortunately, though, because the system tended to be very complex, we didn't sell as many systems as we'd hoped. And so I ended up looking for a new job and found one at the Olympic Training Center. Again, after 20 years or more of being away from the USOPC, I found a job as senior sport technologist at the Olympic Training Center in Chula Vista, California. And as you can see, beautiful outdoor facility. My job was working mostly with track and field, mostly with the throwers and the jumpers. So because of the fact that we were outside, we didn't use the motion analysis systems anymore because the optical-based motion analysis systems definitely don't work very well outside. And the electromagnetic system, one of the disadvantages that I forgot to mention was that it's wired and it's tethered. So it didn't really work with any sports that were moving, such as running or jumping. It did work with golf and baseball because there's not as much motion and they stay pretty much in one spot. So anyway, we got on to using inertial sensors, and here's an example. Again, I mentioned the kinematic sequence. So here's an example of the kinematic sequence in javelin. In this case, we have a sensor on the pelvis, and we have a sensor on the shoulders. And so with just those two sensors, which you can see don't interfere too much with the athlete because they're wireless, we were able to measure the X factor, which is the separation between the upper and the lower body. We could measure the X factor and the X factor stretch. We can measure sequence and timing. And so if you look at the graph, we've got, again, the red one is the pelvis and the green one is the rib cage. So again, we can see what kind of acceleration they've got because that's the slope of the curve. We can get how much stretch they've got. That's that little area under the curve here. And we can see how much speed gain. So if the green one was sitting on top of the red one, that means that they haven't got any speed gain across the torso, across the midsection of the body with the abs. And so one major part of their power generation is missing. So you can get an idea now how the technology can help us. One other technology that was extremely helpful, and it is motion capture, it's motion capture of the implement. We used a Doppler radar system for throws events, and two technologies there are two companies, TrackMan and FlightScope. You've probably heard of both of those in the baseball and golf industry. Well, we had them adapted to our throwers, specifically for shot put. You can see Ryan Krause here, current Olympic champion and Olympic record holder, throwing the shot put. I think this was at the trials a few years back. But anyway, what the radar would do would just sit behind the ring, so it didn't interfere with the athlete at all. And then it would give us 5 measurements: the distance thrown, the angle of release, the speed of release, the direction of release, and what else? The height of release, yes. And so with those 5 parameters, we're able to determine where the shot put's going to go. So you can imagine now in training sessions at the Olympic Training Center in Chula Vista, we could really quantify their throws. So we could tell them, instead of just saying, oh, that throw was a little bit too flat, we could give them exactly the angle of release. You need to speed up a little bit. We can say you need to speed up by 2 or 3 meters per second, or whatever the number would be. And we know that to throw an Olympic or world record, you need to be around 14 and 14.5 meters per second. So we know exactly, we've quantified it. So that's another example of how we've used the technology, the motion capture technology, at the Olympic Training Center. So our technology philosophy, and I've kind of alluded to this already, is it must not affect the athlete while they're training. It's got to be non-intrusive. It's got to be invisible to the athlete. It's got to be easy to use and simple to understand. And like I said before, if we can give them immediate feedback or even real-time feedback, that's even better, because then they can relate the feel in the last trial or in the last skill to what actually happened. It also needs to be accessible on a variety of devices, and it's got to be accurate and inexpensive. Now, to me, the point of being accurate is extremely important. I've heard people say, oh, it doesn't have to be totally accurate, it doesn't have to be research quality for training, just has to give you an idea. Well, I beg to differ on that point, because if now you're going to tell an athlete that this trial was different than this trial, and you don't know whether that's within the vicinity of the error of the system, then you could be telling them there's something different when it wasn't different, because it was just an error in the measurement system. So to me, accuracy is key in any technology that you evaluate. So motion capture and powered by AI was the topic of my presentation. So let's get into some of the new systems that we're looking at and using at the US Olympic Committee, and they will provide these benefits that I just talked about. So at the US Olympic Committee, we're very, very lucky to be sponsored by a tech and innovation group from Silicon Valley and industry leaders around the country. They are basically donating to the US Olympic Committee and Paralympic Committee and funding the technology and innovation group. And we have what we call big vision initiatives, initiatives where the technology is going to help multiple sports, not just one or two. If it can be used across sports, then obviously it's much, much more beneficial. And motion capture and analysis with AI is definitely one of those technologies that we're looking into. And I'll give you a few examples. But first, let's talk a little bit about how it works. Well, we call it in biomechanics, we call it markerless motion capture. But basically, it's really what's called these days pose estimation. Effectively, as you can see, the camera takes the image and overlays a stick figure on what it thinks the human form is. And it puts the dots, if you like, at the joint centers and joins them up with the stick figure. So that now allows us to do essentially what we did 40 years ago manually, that is touching all the points of the body. It allows us to do that automatically. The other thing it allows us to do is leave the athlete alone. All we have to do is point a camera at them, and they're certainly used to being filmed. So with that camera and with no intervention, we can get the type of data that we've gotten from sensors, from optical motion capture systems, from electromagnetic motion capture systems. So it's a step in the right direction. Not quite there yet, but getting very, very close. A couple of the problems is we need a large data set to train the machine language algorithms. And the problem with that is currently we're using what's called the COCO data set, which is a general data set that's being collected from normal human motions. And of course, athletes don't do normal motions, especially if you're a diver doing a flip or you're a shot putter doing a spin throw. Those are not motions that the machine language COCO set understands. So we have to collect our own data sets and start training the algorithms. And that can be time consuming and expensive. Other thing that can happen is sometimes they can get confused with the background. If there's lots of people, lots of spectators, we've got to isolate the actual athlete. So anyway, that's the way we're going. We're heading off into pose estimation using artificial intelligence and machine learning. And here's a couple of examples. One of the major projects we're working with is with USA Diving on a project called VAMA, Video Automatic Motion Analysis, with a company called Southwest Research Institute out of San Antonio, Texas. And we're doing diving skill analysis. We're doing it in 2 dimensions, assuming that the motion is in what we call the sagittal plane. So we're filming perpendicular to the point of view. And that gives us enough information to get such things as how far did they push the diving board down? What was the angle of takeoff? What was the height of the dive? What was the spin rate? What was the distance of their head as they pass by the diving board? All of these are very important parameters for both training and competition. And again, as I mentioned with golf, we can compare their good dives with their bad dives, or we can compare a national champion to a world champion and give them directly information on what differences are. Here's a specific example of one I did recently with one of our national team members, Andrew Capobianco, who's given me permission to share this data. He's doing a forward 4.5 somersault. That's 4.5 flips from the 3-meter diving board. And it's a very, very high degree of difficulty dive, which can score a lot of points or can fail pretty easily. Now, we've put 2 side by side and we've drawn the stick figure automatically, and we've calculated the center of gravity. And so you can see this line here is from the center of gravity. This one on the left has a B standing for bogey, and this one on the right has an E standing for eagle. The coach likes to quantify his dives in golf terminology since he's a mad keen golfer. So anyway, the bogey, you can see down here that this white arrow shows you, the length of the white arrow shows you how far away the center of gravity is from his feet. In this one, you can see the center of gravity distance is much smaller. So this one's going to go much further out and it's not going to go as high. This one's going to go higher, giving him more time in the air to complete the dive. So this one, being the eagle, was one of his best dives, and it got in vertically perfectly. This one landed very short. So now he can see the difference, and we can do a biomechanical analysis of all the key points in the dive and help them get their new and more difficult dives ready for Tokyo. We've only got a few months left because you don't want to learn any new dives too close to the competition. Okay, so another project we're working on is called the 3DAT project, and that's 3D athlete tracking. And we're working with Intel on this project, and Intel is one of our top sponsors. So they are helping us with what's called value in kind, where they're supporting the research. And we're looking at track and field. We're looking at sprints, long jump, shot put, high jump, and hurdles. We started pretty much on long jump because, again, similar to diving, we can do it in 2 dimensions along one plane. So we overlay the stick figure, and now we're able to capture the few steps before the takeoff and the launch into the air. And just like we did in shot put, we're able to tell them what their vertical velocity is and what their horizontal velocity is and how they partition that velocity. Basically, they're changing their incoming running velocity into horizontal and vertical components. And that's what's key in making a jump the longest jump you can possibly do. We don't want to lose a lot of speed on the board. And it's important to get this data back to them quickly because they want to know what that felt like so they can relate the data to what the jump actually felt like. and make a change. Okay, let's look at weightlifting. We're currently working on this project as we speak. Microsoft and USA Weightlifting are in the middle of a hackathon right now, and today's the last day of the hackathon. And the goal is to be able to do this automatically. Currently, they're manually digitizing point by point still, and we want to do it automatically on a cell phone or an iPhone. And we're going to look at the trajectory of the end of the bar during a lift. Obviously, we don't want too much horizontal motion. Up and down motion is more efficient, and cutting down the horizontal motion as much as we can. A couple of the other things we're looking at is the vertical force that the lifter is putting onto the bar and the bar velocity, as well as a couple of metrics at specific phases in the lift. So we're excited about this, and we're excited at getting the help from Microsoft to get this up and running automatically. Now, this is a different example because now we're not just looking at motion capture from the point of view of biomechanics, we're looking at it from the point of tagging. So that the process of tagging is really just going through the video and identifying different things that are happening in this case, a boxing match. When were they throwing a punch? What punch were they throwing? When were they advancing? When were they retreating? Where were they on the mat? When were they on the ropes? All of these things are very important to the coach. And in the past, we've been doing this manually. Literally, a person has been sitting there going through the video and tagging each one of these and writing down the frame number at which each one of these occurred. And that can take 3 or 4 hours per match or per bout. Now, with automatic tracking and AI, artificial intelligence, we can do it much, much more quickly. And we're thankful to Orbit Shifters for helping us on this particular project. And that's going to add a lot to our boxing knowledge, if you like. So there's a couple of systems. Another example is a company called Uplift Labs. And what I like about this technology is they are democratizing it so that it will be much less expensive and much easier to set up and use. The system basically can use 2 cameras, and they could be iPhones on tripods, one a back view, one a front view, or back view and side view. And the athlete can be set up within 30 seconds. Currently, they've got golf analysis and baseball analysis, but you can see that it should be very applicable to other Olympic sports, such as the throws events that I work in and that I'm interested in. And also, you can see we've got kinematic sequence going on here as well. On this side of the screen, we have different joint angles and different velocity curves. So this is going to be very powerful. It can be uploaded to the cloud and served out to the coach and the athlete very, very quickly. Looking forward to working with Uplift Labs on that project in the near future. Finally, gymnastics judging system. As a gymnast, I was always frustrated when I got a score that I didn't think I deserved. I thought I deserved more. And that's because gymnastics is a subjective sport. Of course, the athlete always think they deserve more. But so we've got figure skating, we've got diving, we've got gymnastics, and they're all kind of subjective sports. But now Fujitsu out of Japan has developed a technology using laser cameras that basically reflect a point cloud back to the sensor, and that point cloud allows them to fit a skeleton or a stick figure using neural networks again and artificial intelligence. And so once they've got the stick figure motion, then they can determine exactly what skills the gymnast is doing, so they can use it to do 2 things. Was the skill performed correctly? Was it the right height? Was it the right angle, etc.? And did they perform the skill, and what was the degree of difficulty of that skill? So it can compile all the skills from their routine and give them a total difficulty score. And basically at the moment they're using it to augment the judges, but in the near future, at least for the difficulty score, it may be able to supplant the judge. The Federation of International Gymnastics, FIG, has a rule book, and all the skills that you can do are in the rule book. And these skills can be compared to the real rule book, and that's how we end up with a skill value or a difficulty value in the end. So this is very exciting technology. It was used in the World Championships last year and will be used at the Olympic Games next year. So, in summary, it seems like we've gone complete circle from 40 years ago, where we were doing markerless motion tracking way back 40 years ago. The only difference, we were doing it by manual methods and a person had to do the tracking. Now we can use AI to do the markerless motion capture. And in my opinion, we're close to the holy grail. I like to call it the magic camera. We point the camera at the athlete, puts the stick figure on the image, and gives us the data without interfering with the athlete at all. So thank you for listening. If you've got any questions, there's my email address. Be good and hopefully stay safe and healthy. Thank you.
Thank you, Dr. Cheetham. Dan Kaufman, Sport Techies Managing Director, here once again to close out the day. I want to thank everyone for attending. We very much appreciate that you've joined us today. I want to especially thank our speakers, Meredith, Phil, Constantine, Marcus. Let's see, who else we got? David, Kristen, Mateo, Greg, Phil Wagner, or two Phils, Phil Wagner and Phil Cheetham, and Mike Weinstein. Thank you all very much. We really appreciate your time. We literally could not do this without you. And I know that everyone in the audience would be giving you a round of applause right now. So thank you very much for your time. What's next? Let's see. We have what's next for today, and we also have what's next down the line for Sport Techie when it comes to events. So first of all, in about 8 minutes, we have a networking session that will open up. And in fact, you can open up and do networking right now if you'd like. But we have targeted networking sessions in 8 minutes at 4:40 Eastern time. One of those is for our pro members, and that is a Q&A with Dr. Phil Cheetham. So our pro members will be able to access that at 4:40, maybe even slightly before. And then the other one is a happy hour that I will be in along with Sport Techie's co-founder and CEO, Taylor Bloom. So please join us there. We'd love to see you, and we'd love to chat with you. Couple other things I want to mention. If you enjoyed this session today, great. And we'd love to have you at other events. Please go to events.sporttechie.com and check out what we've got in store. Sports Capital Symposium is up next. That is in September 17th and 18th. It will be virtual and it will be great. We've got tremendous speakers lined up for that as well. We're expecting thousands of attendees from all over the world to be there with us. So make sure you check that out. And also check out Sport Techie Live. If you have not been to a Sport Techie Live session, we've had some great success with Sport Techie Live. Sport Techie Live is weekly conversations in webinar format with industry experts. Very engaging and conversational for our attendees. Go to live.sporttechie.com for more info there. And last but not least, I want to give a big thank you to our partners for this event, FitLight and Beyond Sports. Thank you very much. We also could not do it without you, and we greatly appreciate the time that you gave us today to present. So thank you everyone for being here. I will jump into the happy hour momentarily, and I look forward to seeing you there. Have a great day.